Great. Great. So let's briefly remember remember our discussion from yesterday. In our discussion from yesterday, I won't write any equations. We studied the quantum mechanics of a particle in one dimension, moving in one dimension. The quantum mechanics was of a particle moving in one dimension, but there were two spin-type degrees of freedom. So the wave function was a two-component. We wrote down a Hamiltonian just out of our heads. The Hamiltonian is parameterized by one function of the position. And with that Hamiltonian, we then explained that that Hamiltonian could be written as the square of a supercharge. More precisely, as the square of two supercharges. So that Hamiltonian was Q1 squared. It was also Q2 squared. Okay, up to some factors of 2. We explained that this model had a sort of generalization of the standard symmetry structure of a system with continuous symmetries, in the sense that there were two kinds of generators in the theory: the odd fermionic charges, which were Q's, and the even or bosonic charges, which were H. There was closure of the algebra when you took anti-commutators of two fermionic charges and commutators of fermionic with bosonic or bosonic with bosonic charges. Okay. Now, this symmetry was sort of unusual in the sense that it was a symmetry that involved the Hamiltonian of the theory. A normal kind of symmetry, so this symmetry is called supersymmetry, as I may not have emphasized enough. This is supersymmetry. Okay. A normal kind of symmetry, the kind of symmetries we're familiar with. For instance, the hydrogen atom, we've got SO3. We've got SO3 symmetry. SO3 symmetry gives us multiplets of states, all of which have the same energy, because the SO3 symmetry generators commute with the Hamiltonian. That's why the spectrum of the hydrogen atom appears in representations of SO3. Okay? So while it organizes states in representations of the algebra, all of which have the same energy, it doesn't constrain the energies of states. You know, you couldn't deduce from the SO3 symmetry that the hydrogen atom would have a ground state at whatever value it does. Okay? Supersymmetry is different in the sense that it's a symmetry algebra that involves in a non-trivial way the Hamiltonian itself. Okay? And so you can use it to make predictions about energies of states. Or to put constraints on energies of states. And we studied an example of that in the last class, again in our toy model. In our toy model, we had we decided to ask how many zero energy states we had. We could solve that problem by just integrating the first order Schrodinger equation. We found the answer was always either 0 or 1. It was 1 when the superpotential went from -infinity to infinity, restricting for the moment to potentials such that W squared blew up at infinity. And it was 0 if the potential went from infinity to infinity or -infinity to -infinity. We discussed this problem in the semi-classical approximation. In the semi-classical approximation, we found that there were as many ground states, as many zero energy states, as the number of times W cut the axis. However, we found, when we understood what we meant by fermion number, that these states came with alternating fermion number. And so, though the semi-classical approximation sometimes badly got the number of ground states wrong, it got another quantity, namely trace -1 to the power f times spectrum of ground states correct. Okay? And this quantity, I may not have again emphasized enough, has a name. This -1 to the power f e to the power minus beta h. This quantity only falsely depends on beta. It's actually independent of beta because only zero energy states contribute to it. It's called the Witten index. Okay? And the Witten index is used as a diagnostic to see whether a supersymmetric quantum mechanics model, or more generally, we'll soon generalize to quantum field theory, a supersymmetric quantum field theory model either breaks or does not spontaneously break supersymmetry. Oh, so what do those words mean? You see, a theory breaks. When do we say that a theory has a symmetry in its vacuum? A theory has a symmetry in its vacuum if the vacuum is annihilated by the symmetries of the theorem. So using the standard terminology, we will say that a theory does not break supersymmetry if all the supercharges annihilate its vacuum. But as we saw in the last class, supercharges annihilating the vacuum meant that the vacuum energy was 0. So the question of whether supersymmetry is broken or not is the same as the question of whether the vacuum the energy of the vacuum state is 0 or not. Because 0 energy states and states that are annihilated by supersymmetry are just the same thing. Okay? So in our model, one way of stating the conclusion of our model was that superpotentials of this form do not break supersymmetry. Whereas superpotentials of this form break supersymmetry. Okay. At the end of the last class, there was some discussion of the circle. Now, I just one quick comment, and we can continue this in the discussion section if you want. But as Subrat pointed out in the last thing, if by the circle we mean x is the same as x plus 2 pi, then since w of x and this term enters the Hamiltonian itself, if we want to impose anti-periodicity, as Songmin was suggesting, on this Hamiltonian, and anti-periodicity such that, for instance, psi is equal to psi of x plus 2 pi is equal to minus, I don't know, w. Maybe the question was w of x plus 2 pi is equal to minus w of x. The only way that this will work, if it's imposed at every point on the circle, is if w is a constant. Right? Now, so this doesn't quite work. So there are other things one could try. One could try to put boundary conditions on an interval, and there are many things one could try. But we'll leave such discussions for the discussion section if people are interested. Okay? There's something else to say about the periodic circle also, but again, I'll leave it for the discussion section. Okay. That's it. That's it for my summary. Any questions or comments before I proceed? Yes. One can consider two particles. Yeah, that's right, or a particle moving in a higher dimensional space. Yes, one can do that. One can do that. I'm not going to do it in this context, but okay. Since this question has come up. You see, the question of how many dimensions the particle moves in, or how many particles there are, is related. And the number of supersymmetries is related but distinct questions. So since this question has come up, okay, let me say something that will address your question. But first, before doing that, I want to go through one little technical detail again about the supersymmetric quantum mechanics that will be useful to know in our fourth lecture. This technical detail is about something called superspace. Okay. So the question we're going to ask ourselves is the following. If you remember, at the end of the last class, we had a Lagrangian. Okay, our Lagrangian was L is equal to x dot squared by 2 minus w squared by 2 plus psi plus I times, or maybe minus I times psi star dot plus psi star dot psi plus plus minus psi star w prime. Okay, this was a Lagrangian for our supersymmetric quantum mechanical model, and we claimed that this theory was supersymmetric. Now, there's something a bit irritating about our discussion. Because though we've checked explicitly that the theory is supersymmetric by constructing the supercharges and so on, it's not manifest by looking at this Lagrangian. You look at this Lagrangian, and this Lagrangian looks pretty much like the same Lagrangian if I replaced this factor, this term, but let's say I added a factor of 2 here. You wouldn't really be able to tell the difference, right? On the other hand, the Lagrangian with precisely these numbers is supersymmetric, and the Lagrangian with the 2 is not. Okay? Now, how do we know that? For Lorentz invariance, whether a system is Lorentz invariant or not is governed by very simple principles, right? You write down an action, and that action is written down in a way that is manifestly Lorentz invariant. You look at the action and you're looking at a Lorentz invariant system. Wouldn't it be nice if we had a way of doing the same thing for supersymmetry? Wouldn't it be nice if we could try to see that this action here was supersymmetric by I? Okay? Wouldn't it be nice if we could see that this action was supersymmetric by I, rather than just by inspection? Okay? And there is a way of doing it, and there is a way of seeing this, which I'm now going to briefly review for you. Okay? And that goes as follows. Okay. So firstly, let's go back to our Hamiltonian picture. In our Hamiltonian picture, we had sigma, q was equal to sigma plus by 2 in a p minus I omega, and q bar was equal to sigma minus by 2 in a p plus I w. These were our supercharges. Now in this Lagrangian language, if you remember, our prescription was that sigma plus by 2 went to psi, and sigma minus by 2 went to psi star. Remember psi star, the anti-commutator was 1, which was the same as the anti-commutator of sigma plus and sigma minus. So we made the identification psi was sigma plus and psi bar was sigma minus. Okay, do you remember this? Okay, so if we wanted to write down this supercharge in the language of psi and psi star, that's simply that q is equal to psi, p minus I w, and q bar was equal to psi star, or q star is equal to psi star, p plus I w. Okay, I've not done anything. Okay. Now, either in this language or in this language, but I'm going to work in this language because it's nearer to the Lagrangian, which I'm going to use for this superspace discussion. Okay, we could now ask, what is the action of Q on every field of the problem? Okay. So what is the action of Q on, what are the fields of the problem? The x, psi, and psi star. So what is the action of Q on every field problem? So let's work out a couple of examples and then I'll write it for you. Okay. So let's see. So suppose I wanted to find what is Q with psi. The anti-commutator of Q with psi. Can somebody tell me what that is? I'll write down the basic anti-commutation relations. Psi with psi star was equal to 1. Psi with psi is equal to 0. Psi star with psi star is equal to 0. Exactly. So, and of course, x's and psi's live in different Hilbert spaces. Okay. So this quantity here is just 0. Because psi with psi, psi just goes through psi. It's the same operator anyhow. I mean, for many reasons it's 0. Okay, so any operator commutes with itself. Okay. On the other hand, what is Q with psi star? This is less trivial. Okay. This operator here goes along for the ride. It lives in a different Hilbert space. So this is equal to P minus I W, where we've used this anti-commutation relation. Is this clear? Okay. And there's one more example. Let's work out what Q with X is. And now I will take the commutator. Because the rule always is that when we've got two fermionic elements, we look at anti-commutators. where we've got either one bosonic and one fermionic or two bosonic elements, we look at commutators. Okay, so what is Q with X? Well, psi goes along for the ride. W and X commute with each other, because W is a function of X. But P and X don't commute with each other. P commutator X, this is of exactly, so this was equal to minus I, so minus I, into minus I. Is this clear? Because the P with the X gives us a minus I, and psi goes along for the ride. Okay? See, it's a very simple game. You know, following this game, I'm going to write down all the non-trivial commutation relations for you. So we'll generalize this Q bar with X is equal to minus I psi bar. We had this, obviously, Q bar with psi bar, or psi star. Sorry, I'll interchangeably use bar and star, just to confuse you. Okay, this is equal to 0. And we have the other non-trivial one is Q bar with psi bar. Sorry, Q bar with psi is equal to P plus I. Oh my God. Right? Okay. Now what I'm going to do is encode these commutation relations. Now what I'm going to do is to encode these commutation and anti-commutation relations into some sort of differential algebra. Okay? And this differential algebra will involve non-commuting or anti-commuting variables. So what I do is, quite a marvelous trick. The thing I do is this. I say, let me define what I'm going to call a superfield. The superfield is X, capital X, to distinguish it from small x, which was a bosonic coordinate. Okay? And this is going to be defined as X plus theta psi bar plus theta bar psi plus theta theta bar F. That's right. Psi was always a Grassmann number. Now I'm inventing two new Grassmann numbers in the problem. Theta and theta bar. So I always had psi and psi bar. Now I add to the game theta and theta bar. In the Hamiltonian, psi is an operator, but in this Lagrangian, the thing that we will quantize to get that Hamiltonian, it's a Grassmann number. Okay? That's right. So now, what we're going to be doing is to try to rewrite this classical Lagrangian in terms of superfields. In that classical Lagrangian, the thing that we're going to use for a path integral, psi is just a C number, a Grassmann variable. Okay? So from that point of view, just for the classical Lagrangian, psi and theta are on equal footing. They're both Grassmann numbers. Theta is in my head. It's not in physics. I've just invented it. Okay, I put it in for fun. Okay, now what is the point of this theta? The point of this theta is, see, I've had to do something a little unpleasant here. I've had to add, so what I did was to invent two Grassmann numbers, theta and theta bar, and then I just wrote the most general function I could of these two Grassmann numbers. Okay? You might ask, well, this doesn't look like the most general function of two numbers. If I have a real number, and I look at the most general function, I can Taylor series expand it to arbitrary order and a derivative expansion. But you see, Grassmann numbers have the wonderful property that they square to 0. So the Taylor series expansion of any function of Grassmann numbers ends at first order in every variable. Okay? So the most general Taylor expansion of a function of theta and theta bar is of this form. There's nothing more general you can write down. This is the most general function of theta and theta bar. No, what I've done is here the coefficient of theta I'm defining as psi bar. The coefficient of psi bar I'm defining as theta bar I'm defining as psi. And the coefficient of theta bar, which is the other term, I'm just defining as a new field. Dynamic will tell me whether this is going to be related to old fields.
This is an expansion of theta bar.
Exactly. It's an expansion of theta bar. And the coefficients of that, I'm using some foresight. Or just by my definitions, I'm identifying different coefficients of different fields. These will turn out to be the same fields as x psi bar. And this last one is something unpleasant. Because you see, in our dynamical problem, we had only three fields. We had theta, psi, and psi bar. But if I wrote down the most general function of these theta and theta bar, if I try to write down the most general function of this theta and theta bar, okay, then if I try to write down the most general function of this theta and theta bar, then I need a coefficient of theta bar itself. That's not there in our dynamics, but I'm going to put it in anyway because, you know, analysis requires it. This is what's going to be called an auxiliary field. You know, a field that is not dynamical, and hopefully our equation will tell us what it is. Yes? Of theta and theta bar? You see, these theta and theta bar are very formal objects. Okay, the best way to think of these theta and theta bar are, for instance, their algebra is exactly the algebra of sigma plus and sigma minus. Okay, so any function of theta and theta bar, a function of these 2 cross 2 matrices, sigma plus and sigma minus on a 2 cross 2 space. One way of thinking of the problem. And then there are just so many functions you can write down of 2 cross 2 matrices. Okay? Yeah, these are formal objects, their fractional square roots are not defined. Okay, a function of this is defined as a Taylor expansion. Okay. Yes? There was a non-trivial commutation between Q and P as well. That's correct. I haven't written it down. You're absolutely right. As this is a good point. So the non-trivial commutation between Q and P will involve derivative of this function W with some factor of I. Sorry, I should have written that down. The reason I haven't written down is that in my Lagrangian P does not appear. I'm going to try to generate all of these relations using superspace. So that was not important for me. But you're right. Logically, I should. Thank you. Other questions or comments? What? Theta, one component, just one theta. It's not theta alpha, it's just theta. It's one anti-commuting number. Theta bar is a second anti-commuting number. No, psi and psi bar, well, it has two components if you put psi and psi bar together. Remember, psi and psi star here were just independent anti-commuting numbers. And the quantization of this system gave us this algebra, which then produced the two-component wave function. Okay? So there are two different psis one should not mix up. One is the wave function psi, which is a two-component wave function. And I used the same symbol for that yesterday. The second is this anti-commuting number, which is a totally different thing. So I'm sorry about that. You understand? Here, psi and psi bar are just one component objects. Great. It's great you clear up all your confusion. Any other questions or comments? That one can also do. So the question is, could you write down a fermionic superfield, which starts off with some fermionic number and then at order theta has bosonic things? That one can also do, and in some situations is useful to do. Will not prove useful for me. This is the trick that will prove useful for me. I'll stick to this, but in principle. No, there's no general guiding principle. The general guiding principle is you do what is useful. Yeah, I don't think it's useful. Yeah, I think that's the fair guiding principle. Okay. Now, the next question I'm going to ask is the following. I'm going to ask, can we write the action of supersymmetry? Okay? Can we write down the action of supersymmetry as some sort of differential operator on this field X? Okay? So what do I mean? What I want is the following. I want delta X, so the variation of X under supersymmetry, which by definition means delta x plus theta delta psi bar plus theta bar delta psi plus theta theta bar delta f. This is my definition of delta x. How the whole superfield varies under supersymmetry. I want to write this as equal to some differential operator q do. I'm writing differential operator. Okay, I'm using the same symbol as this q, but here this was an abstract operator on the Hilbert space. Here this is a concrete differential operator acting on superfields. Okay, I want to write this as this acting on the on x. Question: can I do it? Okay. And the answer is, well, what do I have to do? I have to get this q acting on the superfield. When I get this q acting on the superfield and equate coefficients of theta in the theta theta bar expansion to see if I've got it right. Okay. Can I invent some sort of differential operator? But that will do the job. Okay. So night before last, I tried to do it, and if I haven't messed up, I found the following answers. Theta bar. Let us check that this is correct, remembering that P, which P was equal to x dot from canonical commutation relations. Okay, let's check that this is correct. Okay, so in order to check this, what I'm going to do is to just, let's take Q as an example. I'm just going to write down Q acting on x. So we have Q acting on x. Okay, so we have Q acting on x. That is equal to what? So that is by definition theta del by del t minus I del by del theta acting on x plus theta psi bar plus theta bar psi plus theta theta bar f. Thank you. Thank you. Okay, now let's just work this out. Let's just work this out term by term. See, this del by del t term cannot act on any term that already has a theta, because then we'll get theta square. Okay, so the only term that it can act on is this guy and this guy. Is this clear? Acting on this guy gives us, so the first term is x dot theta, and the second term is plus theta theta bar plus theta theta bar psi dot. Is this clear? Okay. What about this guy? Okay, this guy cannot act on a term that does not have a theta bar, because then del by del theta bar is 0. So what can it act on? Well, I'll remove this underlining. What it can act on is this guy and this guy. Okay, so let's see what we get when we act on this guy. We get minus I psi. And here we have to be careful, because here, exactly. Here we're going to take the del by del theta bar through the theta before hitting the theta bar. So this will become plus I theta f. Okay. Now we have to compare this with what you see. What we are supposed to do is to take this and write that compare this term by term with the change of the various fields in the superfield under supersymmetry. So, if this is correct, it tells me that delta x is equal to minus I psi, because the coefficient with minus I psi. Okay, so that one was good. Check. What about delta psi? Delta psi was the coefficient of theta bar, which is equal to 0. Good. What about delta psi bar? Delta psi bar was the coefficient of theta, which is equal to x dot minus if plus if. Okay. Now, delta psi bar was supposed to be p, okay, plus this minus iw. So if it turns out that this f is identified with w in some way up to a sign, then we will have got the supersymmetric relations right. Okay, so now at this stage we could do two things. Either we could just replace this f by the right w, function of w, the right w, or we could do something that's even more satisfying. That's the thing that I will at least briefly indicate. We're spending too much time, so I may have to hurry up a bit, but I at least briefly indicate to you. Even this relationship can be made to come out of dynamics, which is very satisfying. So at the moment, I'll just leave it at this. Okay, and remember that if f was equal to minus w, if f was equal to minus w, then I'm getting everything right. Okay, similarly with the q bar, that will leave for you to check. Okay. Now the next step in our program. What we've managed to do is to implement the supersymmetric transformation properties, okay, by some sort of differential operator acting on a superfield. Now, what I want to try to do is to write down an action that will be manifestly supersymmetric. How do I do that? I'm going to use the superfield, but how do I use that superfield to try to write down a manifestly supersymmetric action? Please. How do I get delta f? It's here. Delta f is equal to psi dot. Now, how will this is going to come again from an equation. You will see in our Lagrangian. This will again come from an equation of motion in the Lagrangian. There are two things. You see, we're going to have a term in the Lagrangian which will involve which will involve psi bar w prime. Okay. There's also a term which is psi bar psi dot. Okay. So the equation of motion with respect to psi bar will set psi dot is equal to psi bar w prime. That it will work out, but yes. Okay, thank you, but it's a good question. Okay, excellent. So now what we're going to do, at this stage what we're going to do is now try to find a way of writing down a Lagrangian that is automatically supersymmetric. Now, in order to do that, I note the following thing. See, this Q operator, okay, which was defined in this way, associated with the Q operator, I'm going to define an operator which I call D. Okay, which is theta del by del t minus I del by del theta bar. Sorry, that was minus there, so I'll put a plus I. And similarly, I'll define the operator d bar, okay, which is equal to theta bar del by del t plus I del by del theta. Is this clear? Now, what is the point of this definition? The point of this definition is something interesting. See, already right at the beginning of this lecture, I could have, right at the beginning of this discussion, I could have done one thing. I could have immediately tried to check whether this differential operator obeys the supersymmetry algebra. Okay? By which I mean, is it true that q squared is equal to 0? That's obvious. This part is obvious, right? Because q squared involves either okay. Is it true that q squared is equal to 0, q bar squared is equal to 0, and anti-commutator of q with q bar is equal to whatever it should be, minus I del by del t? Is this true? This guy and this guy are sort of immediately obvious. Let's check this guy. Okay. So let's check the anti-commutator of q with q bar. So we have theta del by del t minus I del by del theta acting on theta bar del by del t minus I del by del theta plus the reverse. Maybe this is supposed to come with a 2, I can't remember. We'll see what comes with. Plus theta bar del by del t minus I del by del theta bar acting on theta del by del t minus I del by del theta bar. Okay. So, look at this term, for instance. This term with this term. This term with this term, and this term with this term. Both of them are del by del t squared. Both of them have a theta and the theta bar. But one has the order theta theta bar, the other has the order theta bar theta. So that just gives you 0. Okay? Similarly, if you look, for instance, at this term. Both of them have two derivatives, one with respect to theta and the other with respect to theta bar, but they come in opposite orders, so that gives you 0. Okay? Where do we get anything non-trivial? We get anything non-trivial only when this derivative hits this theta bar. That's why q squared was trivially 0. Because the derivative and the theta never were the same thing. Okay? So we get something non-trivial when this guy hits this, or when this guy hits this. And now, what have I messed up here? But this was theta. That was theta, right? This guy hits this. So what do we get when that happens? We get minus I del by del t with a 2. You see? So we've checked at the level of differential operators that these differential operators for q and q bar obey the algebra expected of supersymmetry. This is a consistency check. Okay, so these differential operators consistently implement the supersymmetry algebra. However, now what would happen if I computed d theta q theta bar? Okay, the only thing in this calculation that's changed is this sign. And now these two derivatives that had the chance of giving us something non-trivial, the two derivatives, one of them comes with a plus sign, and the other comes with a minus sign, and so we get 0. Okay? So this operator D was invented so that it anti-commutes with the supersymmetries. This is equal to 0, and of course it's very easy to see that D, so all these, d theta with q theta is equal to 0, and similarly d theta bar and so on. All these anti-commute with all theta, or all q's. Okay? All these anti-commute with all q's. And did I define D by flipping this sign? I defined it by flipping that sign. It's also easy to see that the D's give you a similar algebra to the supersymmetry algebra, though we won't use that. Okay? Now, why is this important? This is important because of the following. This is important because of the following. Suppose I consider the following action. d2 theta, d theta x, d theta bar x. Maybe by 2. What? dt integration also. Thank you. I consider this action. Now I want to know how this action varies under supersymmetry. Okay? So under supersymmetry, let's say I do an infinitesimal supersymmetry variation. Okay? What I have to do is to vary the superfield with the supersymmetry operator. So I get a term which is variation of this field times this, plus this times variation of this field. But now, because of the marvelous property of the anti-commutation of the Q differential operator and the theta differential operator, I can take the Q differential operator outside the D's at the expense of a minus sign for both terms. Okay? And therefore, what I get is the Q differential operator acting on this whole thing times this thing, plus this thing times the Q differential operator acting on this thing. But then by the Leibniz rule, that is the Q differential operator acting on the whole thing. Right? Derivative of A times B plus B times derivative of A is derivative of AB. So it's the Q differential operator on the whole thing. So though I've been a bit fast here, you can convince yourself that this whole thing is integral dt d2 theta delta S. Delta of, which is Q theta of d theta x, d theta bar x, perhaps up to a minus sign. It's proportional to, let me write. Is this clear? Now, I haven't even told you, but what does this d2 theta business mean? What does this d2 theta business mean? I assume you all know it, but just to remind you, d2 theta means in whatever expression you have, pick out the coefficient of theta bar. That's what it means. Integrals in Grassmann variables are the same as differentials with respect to Grassmann variables. Okay? Now this q theta, what was it? Q theta was this object here. So, there is one term which is d by dt times something which would be non-zero. But we have an integral over time, as somebody pointed out. And the integral over time of d by dt gives me a total derivative with appropriate boundary conditions, which is 0. On the other hand, we've got this other term here, which is d by d theta bar. But the integral of a total derivative is 0. That's a fancy way of saying something obvious. What I'm supposed to do by integrating is to pick out the coefficient of theta and theta bar. But that derivative kills a theta bar. After I've taken a theta bar, whatever the original expression was, there is no term with a theta bar left. So the coefficient of theta bar is just 0. And so this quantity acting on any superfield, integrated both over time and theta, just gives me 0. Okay? And therefore is equal to 0. Do you understand? Yes? this in place of this means d theta bar. I don't even, yeah, d theta bar. That's what it means. That's what d2 theta means. Is that the question? Yes. What it means is, whatever your superfield expression is, expand it in a Taylor series in theta and theta bar, and pick out the coefficient of theta bar. That's the meaning of that term. Is something confusing? Please ask again. Why am I integrating over superspace? Yes, why? Because I want to construct an action that will be supersymmetric. See, there are two things to say. Firstly, an action has no thetas and theta bars in them. Right? Theta and theta bar are in our head, not in physics. So we are free to put whatever we want in our heads, but in the end, when we write down an expression of physics, those artificial things should have gone away. Okay? So, I've got stuff with thetas and theta bars, I've got an integral over thetas and theta bars, I'll get something without. But why in this way? Because it works. Yes? Yes? Exactly. That was the next thing I was going to say. Okay? Exactly. And plus with the extra terms that will allow us to set f is equal to whatever it should be. He asked whether this was the same action as the one we started with. It is, and we'll come to that. Is this clear? Okay? So this now is a way of making the supersymmetry, any such action is manifestly supersymmetric. Because the variation of the action under a supersymmetric transformation manifestly gives you 0. Okay? So we've manifestly produced a supersymmetric action. The remaining task is what was asked. Was to, if we've not messed up, we're guaranteed to have obtained a supersymmetric action. Is it the supersymmetric action we started with? So far not. Okay? So far not, but I can't swear. Yeah, right. But if we do the following, if we add plus minus h of x, I can't remember whether it's plus or minus. Okay, where h prime is equal to w. So h is some function of a superfield. That function has the property that its derivative is equal to w. Okay, if we add this term, if we add this term to this action, and then we just open out the action, we evaluate all terms in theta, theta bar, so on, my claim is that you will recover the original action we started with. Okay? This quantity is as supersymmetrically invariant as this quantity. Because remember, we saw that any integral of any superfield, any object that transforms under supersymmetry like a superfield, is invariant under supersymmetry. And any function of a superfield transforms like a superfield. It's also a superfield. Okay. By Leibniz rule, the variation of h of x is q acting on h. Right? For instance, if it's x cube, you understand, right? Leibniz rule. Okay? So, if we complicated the original thing to include some function of x, chose that function appropriately. So that function was tuned to be whatever it was in the related to the w. Then my claim is A, that we will get back the same action, and B, if we're very careful, we'll also get the right supersymmetric transformations. Now I'm not going to try to check this for you in this class in the interests of going beyond quantum mechanics in these lectures. Okay? It would be nice, right, if we would if this is a semester-long course in supersymmetry, we would check all this. And frankly, lectures on supersymmetric quantum field theory is sort of like lectures on quantum field theory. It's a bit ridiculous to give 4 lectures on it, in my opinion. But anyway, we'll do what we can. Okay. Okay. Fine. Okay, so I'm going to leave this as an exercise for you, or we can discuss in the discussion section or something like that, to check that this action, with an appropriate choice of sign here, is the original action that we started out with. Okay? Any questions or comments before we proceed? Okay. So we've learned one new thing in our work through this process. We've learned how to write actions that will be manifestly supersymmetric. Any questions or comments about this? That will be automatic from here. You see the auxiliary field was this. Okay? And when you plug this, so for instance, suppose we didn't have this H. That would be like our original theory, but with W equals 0. And in that theory, we will find that F is just set to 0. When you open out that Lagrangian, you will have a term which is F squared, no term linear in F. Okay? The equation of motion of the Lagrangian will set F is equal to 0. With that H, you will have a term that is F squared, but also a term that is H prime X times F. Can you see that there's a term here? Just to see this. Suppose I try to open out this term. I try to do the d2 theta integral of this term. Okay? Now, what we will get is H of X. What we have to do is to remember that this X is little x plus theta bar psi plus theta psi bar plus theta theta bar F, and do a Taylor series expansion in theta and theta bar. And keep terms only, just do the Taylor series expansion, remembering that Taylor series expansion terminates. Okay? Now there will be one term. Remember, we are interested only in the terms that are theta theta. There will be one term that is first derivative and pulls out the theta theta bar F. So that term will be like H prime of X theta theta bar F. Okay? That is the term that will set F is equal to W with appropriate sign. This will all come out, but we don't have the time to go through it all here. Okay, any other questions or comments? Okay, fine. So let us proceed. The last thing I want to say about quantum mechanics, and I'll keep this to 2 minutes flat, unless there are questions or comments, is related to the question that was asked right at the beginning of the course, beginning of today's lecture. And that question went, that question was as follows. It was, what if you had this particle propagating in a larger number of dimensions? Okay, instead of propagating in one dimension, propagating in many dimensions, can something new and interesting come out? And the question also was, can you get enhanced supersymmetry? And the answer to both these questions is yes. And I want to very briefly tell you about that. See, what we had here was the motion of a particle. It was the motion of a particle in one dimension with some sort of potential, and then souped up version of that. Okay, now, you see, if we've got a two derivative motion of a particle in one dimension, you might wonder, why was this kinetic term so simple? Could we have made a more complicated kinetic term? Well, what we could have tried is some sort of g of x. Let's do the bosonic part. X dot squared. But this isn't anything really new. This isn't anything really new, as you see as follows. Let me make this g of x, and let me make it h. Suppose I find an h such that this is h prime x, the whole thing squared. Then this thing is just h prime squared. So if I do a field redefinition on my Lagrangian, redefining x to h, I go back to x dot squared at the expense of complicating my potential. My potential, which was some function of x, now has to be expressed as a function of h. So in one dimension, two derivative kinetic terms are essentially unique. Okay? The same is not true in higher dimensions. The same is not true in higher dimensions because you can have motion. Because you can have motion on like this, xi dot, xj dot. This kind of motion is possible. This kind of kinetic term is possible. Now we know, you can ask, what about field redefinition? Well, how does a field redefinition of x's change gij? By the Jacobian. Well, gij has indices. According to what famous rule of physics does a field redefinition of xi's change gij? According to the rule invented by Einstein called diffeomorphisms. Gij can be thought of as a metric on xi, xj space. This guy here, x dot, is a tangent vector in the configuration space. So under a field redefinition, this guy transforms like a two lower index object, which is to say that it transforms like a metric under coordinate changes. Right? So, kinetic terms involving more than one field. Kinetic terms involving more than one field here, okay, are characterized by a metric. Now you can ask, can all metrics be brought to each other to some standard form by coordinate transformation? And if you knew nothing about, if you had been asleep over the last 102 years, you might have had a hard time answering this question. But since all of us have taken courses on general relativity, we have an easy time answering this question. The answer to the question is, in a sufficiently large number of dimensions, including two in fact, you cannot bring all metrics to a standard form. So there's actually genuine different information in a metric. This is the theory of manifolds, right? Different manifolds are different because when they have different metrics. Okay? So, there is interesting physics with more than one field to study, even without potential. Just the motion of a particle on a manifold as an arbitrary function of the metric is an interesting problem. Okay? And you can ask, this problem is called the problem of a sigma model. A quantum mechanical sigma model. This would be a bosonic quantum mechanical sigma model. You can ask, is it possible to write down a supersymmetric sigma model? And the answer is yes, it's very easy. Just write d2 theta dt d theta gij, ij of x of the superfield. Okay? D theta xi, d theta bar xj. Okay? This quantity here is manifestly supersymmetric for the reasons that we talked about before. Okay? Moreover, let's look at the dependence, its dependence on little xi's. You see, when I take d theta xi, there is a term which is theta times d by dt. Or was it theta bar? No, theta. Theta times d by dt. And d theta bar has a term which is theta bar times d by dt. So there is a term which has theta bar with x dots, with xi dot, xj dot. So then if I take the part here, which replaces capital X by x, the lowest order in the Taylor expansion, that already has one term with two thetas, the theta bar, in which I've replaced the d by d theta x by xi dot, and d by d theta bar x by xj dot. And so there is one term in the Lagrangian, the term that involves just little xi. This is gij xi dot xj dot the term we wanted, plus other stuff. So it's a supersymmetric generalization of the bosonic sigma model. Okay, this is another quantum mechanical system that is very interesting to study. And I just, 1 or 2 minutes I'll tell you about it, and then we'll proceed. Okay. Okay, I'm going to tell you about it for 1 or 2 minutes and then proceed. And the 1 or 2 things I want to say is the following. Look, in this theory, okay, in this theory, you can ask, you know, these superfields have an xi and they have a psi I. Okay, and you can ask what the supersymmetry generator, what the supersymmetry operator is in this theory. And it's not too difficult to convince yourself that Q goes like psi I pi, and Q bar goes like psi I bar pi bar. Sorry, pi. I'm not going to work out all the details of this, okay? Just going to give you a flavor and move on. The differential operator is the thing that implements the action of the actual Q operator on superfields. What I'm now writing down is the actual Q operator. Okay, this thing is the same as, did we have it somewhere? Oh, we've just rubbed it out. We had an expression which was psi x dot plus p. It's that, the actual operator, the genuine quantum mechanical operator. Okay, great. Fine. Now, because of this commutation, this anti-commutation relation, okay, because of the anti-commutation relation, what are the set of states in the problem? The set of states are functions of x times, you know, each of the psi and psi bars can be thought of as annihilation fermionic operators. Let's start with a vacuum that has no psi bars excited. Then you have states with no psi bars excited times functions. State with 1 psi bar excited times functions. State with 2 psi bars excited and times functions and so on. Consider the state with p psi bars excited. It will have psi bar I1, psi bar I2, psi bar IP, A I1, IP. Okay, each of these which is a function of x. That will be the general structure of that state. Is this clear? I know I'm going very fast, but it shouldn't be so fast that you don't get it. You don't understand at least roughly what I mean. So please stop me if it's not clear. Is this clear? Okay. So the most general state in the problem is made up of p-index antisymmetric objects, which are functions of x. Lower antisymmetric objects which are functions of x. Okay? Now, how does this operator act on this p-index lower antisymmetric object? It adds 1 more psi bar. Exactly. It adds one more psi bar, so it makes it a p plus 1 index or antisymmetric object. And it adds that psi bar coupled with a momentum. Yeah. So that extra index, which is antisymmetrized with all the others, is a momentum index, which is a derivative, which, as Indranil pointed out, is exactly the So if we think of AI to AI1 to IP as a form, then Q bar acts like the exterior derivative D. On the other hand, this Q acts by removing one of the indices and replacing it with a derivative. That is by contraction. By contracting away a derivative. Okay? This is what people sometimes call, I don't know, star D or star D star or something. Hot star, something. No, it's not hot. It's like a derivative. Mathematicians give it a name. Naveen will tell me what the name is. Okay. It doesn't matter. The point is that Q star plus Q star Q is the standard definition of the Laplacian on P forms. Okay? So what we get here is something rather wonderful. We start with this problem here, and we ask, what is the Hilbert space? And the Hilbert space of our problem is the set of P forms on our manifold. P running from 0 up to the dimensionality of the manifold. What is the action of Q? The action of Q is the Q bar is the action is the D operator, the exterior. What is the action of Q star? It's Hermitian conjugate. Okay? What is the action of the Hamiltonian? It's the action of the Laplacian on these manifolds. So what we see here is something rather amazing. What we see is that what we've got is a problem whose quantization produces all forms, and whose Hamiltonian is the Laplacian on the space of forms. What are the zero energy states of the Hamiltonian? They're harmonic forms. Forms that are annihilated by the Laplacian. Okay? Now, mathematicians have a name for how many non-trivial harmonic forms of degree P there are. This is the same as de Rham cohomology, right? I mean, but we won't go into all that. They call this BP. It's called a Petit number. And mathematicians are particularly interested in a particular sum over BP, which is BP minus 1 to the power P. They call this the Euler character of their manifold. Now, let us interpret this mathematical object in terms of our physics. BP was the number of ground states, right, in P forms. But what was the fermion number of a P form of degree P? It was P, because it's created by P fermionic creation operators. What is minus 1 to the power F for P forms? It's minus 1 to the power P. So this quantity is trace e to the power minus beta h times minus 1 to the power F on a Hilbert space, which is the Witten index. So the Witten index of the manifold is the Euler character of the manifold. Okay. The set of zero energy states are the Betti numbers. This beautiful mathematical connection. You see, this is so beautiful that I felt I had to tell you about it. It's so beautiful that even someone like me, who usually is very skeptical of claims of deep mathematical beauty, can't help being moved by it. Okay. Great. So that's all I wanted to say. By the way, so this, now to reply to your question, this is an example of a place where we've increased the number of fields, but we've not increased the amount of supersymmetry. However, you can increase the amount of supersymmetry. You can increase the amount of supersymmetry from the 2 that we have to 4 by making this manifold not just any old manifold, but a kind of special manifold that mathematicians like. Okay? It's a particular kind of complex manifold. I won't go into all of that. It's a bunch of names I would have to throw at you. But you take this manifold and make it not just any old manifold, but manifold endowed with certain structure, and you find that then this sigma model has more supersymmetry. Okay? So in order to, and these special kind of manifolds always occur with a certain minimum number of fields. Okay? So the connection between number of fields and number of supersymmetries, there's a connection, but it's not a tight one. You can have more fields without having additional supersymmetry, but to have additional supersymmetry, you usually need more fields. Okay, so that's how it goes. Okay, that's all I wanted to say about about supersymmetric quantum mechanics. I'm sorry for the time I've taken over it. It's Q and Q bar. That's, I mean, it depends on how you count. I would count that as 2. Okay, yes. Yes. Of the manifold, yes. Right? See, we are getting forms on this manifold. So all these BPs are Betti numbers of that manifold. So this is the Euler character of that manifold. Is this clear? Okay, let's move on. So now we've spent almost 2 whole lectures trying to understand these supersymmetric quantum mechanics. I hope the time has not been wasted, because we've encountered many objects in our study that will be useful for us as we move on, if we ever get there. Useful for us as we move on. The things we've encountered are the supersymmetry algebra, the Witten index, the notion of supersymmetry breaking and ground states, and also superspace formalism for making supersymmetry manifest. All these will be recurring themes in our study, which I've tried to show you in one very simple context, where there are no mysteries, where anyone who understands Schiff can verify everything I've said. Yes? Yes, so we've got on any manifold you can define a P-form. P-forms don't require structure to define. No, I said that so far, the manifold is not special. It's a garden variety manifold. But suppose I further tuned that manifold to be special. Then it's possible that that theory will have additional symmetry. And I'm claiming that if you tune this manifold to be special, for instance, you make it what's called a Kähler manifold. I want to avoid using such words. Okay? You can show that the number of supersymmetries, the amount of supersymmetry is doubled. Or whatever. It increases. Okay? So if you make the manifold special, you get additional supersymmetry. At the moment, nothing special about the manifold. Clear? Okay. So great. So now that we've understood, now that we've had a little peek into the nice things that happen in question? Now that we've had a little peek into the nice things that happen in supersymmetric quantum mechanics, we now want to turn our attention to the study of what we're really here for, namely the study of supersymmetric quantum field theory. Okay? So the first question we have to pose ourselves, the first question we have to address to ourselves is, what algebra, okay, what algebra replaces the quantum mechanical supersymmetric algebra? Let me remind you, the quantum mechanics supersymmetric algebra was Qi, Qj was equal to H. And at first you might think this is very pretty, but it clearly is restricted to quantum mechanics. Because what do you mean by H? In quantum mechanics, there's one time, so there's one Hamiltonian. Well, the defining feature of quantum field theory is that it has Lorentz invariance. We shouldn't be picking out one generator of the Lorentz group. In quantum mechanics, there's one time, so we're not breaking in symmetry, we're picking out one generator. In higher dimensions, if we try to pick out one guy, we'll clearly be violating symmetry. So all this is very nice, you might conclude. But I've just proved the theorem that supersymmetry is restricted to quantum mechanics, doesn't extend to quantum field theory. Let's go home. Okay, this is of course not true. Those are the examples of kinds of theorems people often prove in physics. You make an assumption, it's a stupid assumption, then you prove a theorem, it's a stupid theorem. It's true mathematically, but who cares? Okay. You see, the question we want to ask is, are there interesting generalizations of this algebra? Okay. This is a question that has been studied in great detail. And the answer is very well known. I'm going to explain that answer to you over the next half an hour or so. I hope it's only half an hour or so. Okay? So I want to explain to you how this algebra can generalizes to every dimension. Okay? But in order to do that, I'm going to give you a sneak peek. The sneak peek is that the analogues of Qs will generalize to charges that are spinors under the Lorentz algebra. And the analog of this relationship will generalize into the quantity, one spinor times another will give us a vector with a gamma matrix, gamma mu p mu. That's how we preserve Lorentz invariance. Okay, this will be the analog of the supersymmetry algebra in quantum mechanics. Okay, now I've given you the sneak peek. Once I've given you the sneak peek, it's clear that we cannot proceed unless we know all about spinors in arbitrary dimensions. Okay, so the next 15 minutes will be devoted to a discussion of spinors in an arbitrary number of dimensions. Okay, fine. So let's start. So let's start with Euclidean spinors. So next 10 minutes, Euclidean spinors. Let's really try to finish this by the end of today. Oh, once I've said SOD, I don't need to say Euclidean. Spinors of SOD. This is the question we're interested in. Actually, I'm going to look at spinors of SO2n, and together, in the same sort of breath, SO2n plus 1. Okay? So there are many properties of these spinors that will play a crucial role in even writing down the supersymmetry algebra. So I have to review them, review these properties for you. Okay? The next 60 minutes of our course will be very technical. Okay? Irritatingly technical, full of symbols, full of indices. It won't be as beautiful as the, I'm sorry, but that's how life is, right? If you want to make progress, sometimes you have to deal with indices. Unless you're Witten, but then I'm not Witten. So. Okay. 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 Great. So let us proceed. What is a spinor? Consider a set of, let's say we're doing SO2n. We can add SO2n plus 1 to it later. Mu is equal to 1 to 2n. A set of gamma matrices, gamma mu, gamma nu, such that this is equal to 2 delta mu nu. Okay? We want to find a representation of this algebra. We want to find a representation of this algebra. The representation of this algebra is the space of spinors. This is something all of you know. We are in Euclidean space. So I'm first going to work it out in Euclidean space, and then going to work it out in Lorentzian space. So it's easier in Euclidean space. Once we get that, it's a matter of a few eyes over the place. Okay? Good. So I want to see how the algebra can be irreducibly implemented. And in order to do that, I use a standard trick. What I do is to break up these gammas into gamma I and gamma of n plus I. Let's call it A, and gamma n plus A. A is equal to 1 to n. So I've taken half the gamma matrices, gamma 1 to n, and the other half of the gamma matrix is gamma n plus 1 to 2n. And then what I do is to define gamma A is equal to gamma A plus I gamma A plus n. What? This is little gamma A, so it's a new matrix. Okay? And gamma A bar is equal to gamma A minus I gamma A plus n. I should say that this part of the lecture is following a beautiful paper by Strathedy. Let me write down the reference. The paper is called Extended Poincare Supersymmetry. And it's IJMP A Volume 2, Number 1, 1987, 273 to 300. Can I? Oh, who? This? Can I have like 5 minutes more? Okay. Okay. Barring just means that it's a Hermitian conjugate. So we'll be looking for this algebra, and we will also look at, we will demand the following. So these operators are Hermitian, but now because of this I, these are Hermitian conjugates of each other. That's all it means. You can call it dagger if you want, if you like. Okay. Let me make sure I follow his conventions. He puts an I, a half, so I'll do the same. Okay. Now, by using this commutation relation, it is trivial to check that gamma A, gamma B is equal to 0. Gamma bar A, gamma bar B is equal to 0. And gamma A, gamma bar B is equal to delta AB. In particular, all the little gammas square to 0. All the little gammas square to 0. Okay? And gammas with each other implement the commutation relations of a fermionic harmonic oscillator. Is this clear? Okay. Now that we put it in this form, what is the Hilbert space of this problem? It's obvious. We've got a bunch of n fermionic harmonic oscillators. So we can look at its ground state, or its first excited state, so on. Okay? So what's the dimensionality of this Hilbert space? Well, each oscillator is either occupied or not. There are n of them. So we've got a 2 to the power n dimensional Hilbert space. What's the basis for this Hilbert space? Well, one basis, and the basis we'll use through this part of the discussion, is given as follows. The first state is 0, which is annihilated by all gammas. Okay, for some reason, Strategy chooses gammas to be the creation operators, which sort of offends my sensibilities, but yeah. So 0 is defined such that gamma bar on 0 is equal to 0, gamma A. Okay. Now our basis is given by 0, then gamma A 0, then gamma A, gamma B 0, and so on, up to gamma A1 to gamma AN on 0. Okay. To be really specific, I should give you an ordering here. If I've got two gammas, let me choose for the ordering that the earlier one comes first. It makes no difference because they're related by appropriate minus signs. Because gammas anti-commute with each other. Okay? But anyway, let us, fine. So let's imagine we've chosen a particular ordering. Is this a basis for our Hilbert space? Well, clearly it is. Visually it is. But also you can check by counting the number of elements and number of antisymmetric 0 forms plus number of antisymmetric 1 forms plus number of antisymmetric 2 forms up to number of antisymmetric n forms. Sum it up, you'll check, you'll get 2 to the power n. So the number of basis elements is right. This is the basis we're going to use through the discussion over the next, over the next 2 minutes now and the next 15 minutes next class, okay, for our discussion. Now, in this basis, we want to understand what these operators look like. But it's easy to put them down because gamma A is equal to little gamma A plus gamma A bar. And I times gamma A plus n is equal to little gamma A minus gamma A bar. Right, so we could put in minus I here. Notice that gamma A and gamma A plus n are both Hermitian. But they're Hermitian in different ways. Okay? As we will see, these objects are operators that always have real matrix elements in a basis. Okay? So this quantity is real and symmetric in our basis. Whereas this quantity is imaginary and antisymmetric in our basis. How do you see that little gammas have real matrix elements? Well, we just compute. You take one of these guys, put it on the left, put a little gamma, take another one on the right. You get either 1 or -1 if all the gammas match up. So clearly the matrix elements are real. Is this clear? Okay. So we've chosen a basis in which the first n gammas, these gamma a's, are real and symmetric. What? You want to make Pauli matrices out of this? You can try to represent these as direct products of Pauli matrices. But to get all the symmetry properties so beautifully right is difficult in that representation. There are many alternate representations. This is a particularly convenient one for what I want to do. Okay? So, gamma A, real and symmetric. Gamma A plus n plus a. Imaginary and antisymmetric. Now, it will prove important for me to have an operator that takes a gamma matrix and replaces it by its transpose. So I'm going to define the following. Let C is equal to product, A is equal to 1 to n, gamma n plus a. C inverse gamma mu C is equal to, I'm claiming, and then we'll see in a minute, immediately, -1 to the n, gamma mu transpose. With this definition, that relationship is true. Why is it true? You see, every time you take one gamma through another, you pick up a minus sign unless the gamma is equal to itself, in which case you pick up a plus sign. Why do you pick up a plus sign when you take one gamma through itself? It's because any two operators always commute with each other. That's not a deep thing. The interesting thing is you pick up minus signs when you take gamma through others. Okay? So now let's see, suppose gamma mu is one of these guys. Then the C's are the product of the other gammas. So to get C through here, you have to take this gamma through n other gammas. So you get a factor of -1 to the power n. But these gamma a's were symmetric. So you see this works. Right? Because if I take this through, I get -1 to the power n times the gamma itself. But gamma was gamma transpose. So this works. So for these guys, it works. Is this clear? Yes. There will always be a C. Now, once I found a C, I can perform a similarity transform on any gamma matrix. So algebraic relations will always continue to hold. Okay? So I'm choosing a convenient basis, but then I can transform it, and any algebraic relation like this will continue to hold. Okay? We will always have a C. This is a property of the algebra, not of the basis. Basis is for convenience. Okay, and last thing, and then I stop. I'm sorry for going so far over time. Okay, the last thing is this. Now, suppose these gammas were one of these. Then how many signs do I get when I take C through it? n-1. Because this gamma produces a minus sign through the n-1's gammas in C that are not itself. And produces a plus sign when you take the gamma through itself. So we'll get n-1. But in that case, gamma transpose is minus of gamma. So this relationship also works for those gammas. So now for all gammas, this is true. And the important thing about this relationship is what you said. This kind of statement that where gamma A is real and symmetric for the first n gammas, imaginary and anti-symmetric for that is very basis dependent. But this statement does not rely on breaking up the space of gammas into some spaces. It's true for all gammas, and so will be preserved under similarity transform. Okay, so this is like an invariant statement that is basis independent, even though we derive it in a basis. Okay, great. So we have this nice C operator. I'll say one last thing and I'll stop. I want, in this whole discussion, it's very important to keep track of index structure. Okay? So my conventions will always be that spinors transform with a lower index. Gammas are objects that act on spinors. So they will transform with the first index lower and the second index upper. So that you can multiply a psi b, for instance. Two component, no. This spinor of this SODH. Okay? And what is this now? What is this C object? Okay? This C object is replacing gamma with its transpose. Now the transpose has opposite indices. If gamma had first index down, second index up, the transpose has first index up, second index down. Okay? So you see, C inverse apparently is raising an index, whereas C apparently is lowering an index. So that the structure which was down up will match with this, which is up down. That tells you that the index structure of C should be C alpha beta. Two lower indices. Okay? I'll make the real statement of what this means in the next class, and then we'll proceed. So this C matrix is sometimes called the charge conjugation matrix, or something like that, and it's a very important matrix in everything we'll be doing. I'll stop here. We'll continue and complete our supersymmetry algebra analysis next class. What? Is C unitary? No, not necessarily. Since I have to answer the question. Okay. This is easy to figure out. Let's see. What is C star? Okay. C star is equal to okay. C star is clearly -1 to the power n times C, because it's a product of n real matrices times n imaginary matrices. So the n factors of I. So the I goes to -1 to the power n. Do you understand? Okay. What is C transpose? Maybe I'll do this next class, okay, on the discussion section. Maybe it'll take too long. This was what we next wanted to talk about, but it's not necessarily unitary. C dagger gives you a phase. Depending on what n is, that is either 1 or -1. That's the answer.